This is Completeness Axioms. This is the Big Academy. I want to look at completeness axioms, and these we do them in real analysis, and it's a very key concept. Okay, even an empty subset of S of a real set, which is S, which is a subset of a real set, is bounded above. And that means what? If it's bounded above, then it may have a supremum in the real set. So that's the first axiom of completeness in real analysis. That even an empty subset of S of real set, it is bounded above. And if it's bounded above, then it has a supremum in the real set. Number 2. Every non-empty subset of S in real set is bounded below, and that means it has the infimum in what? In the real set. So you take n subset in S in real set, say S, you'll find it is bounded above, and it has a supremum in R set. And again, you'll find that that set is also bounded on the lower side, which is below, and it has an infimum in R. So those are the two key completeness axioms. For example, let's look at this set. If I say set Z and a negative up there, I mean that it is the negative sign of the integer set. So you find that it is bounded above, and you'll find that its supremum is -1. It's -1 because if you have 0 here, you go -1, -2 that way. So this -1 here is the integer. It's an integer, and it is actually our supremum of this Z, which is also real. Okay. Then the set R, if you take the whole set of real numbers, you find that it does not satisfy the completeness axioms. Why? Because it's neither bounded up above nor bounded below. For example, consider this. Let's consider another number 3. We consider an empty set of rational numbers, which is defined as this. So you find that this one is bounded with supremum of S, which is √2, but that √2 is not a rational number. Remember, it's not a rational number. It is the rational number from our previous tutorial that we normally did here. Okay. Let's look at another key thing, which is called density of irrational numbers. And notice, between n two real numbers, there is a rational number. So between n two real numbers, you take 1, take 2. In between here, there is rational number. And therefore, we say that rational set is dense in real set. In between is dense in real set. That's what. So let's look at this theorem. If x and y are real numbers, with x being less than y, then there exists a r, which is a rational number, such that x is less than r, is also r is less than y, and therefore we say this is what we define as density of rational number set to real set. Okay, so in between, if you have x and y being real numbers, then in between there is a rational number. r. Okay. Again, if we have x and y being real numbers, and with x less than y, then there exists an irrational number w, which w such that this w lies in between x and y. And this is now what we are calling the density of irrational numbers. Density of irrational numbers. Now, how do you prove this? We consider the real numbers. We just work with the definition that we have. So if you have two real numbers, say them, call one x over root p and y over root p, where p is prime, and of course if root of p is irrational. Remember that. And therefore there exists a rational number r such that this is true by our theorem above. So that if you rearrange here, multiplying by root p every part, you'll find this is true. And if you look keenly on this, you'll find that that becomes is a irrational number. And therefore, our proof to that, if we have two real numbers in between, there exists a irrational number, is just done. So kindly subscribe to this channel, share also with your friends so that they get this knowledge, they acquire this knowledge. Yes, until next time.